Hi, I'm Zor. Welcome to Unizor Education. During the last few lectures we were talking about central fields and in particular gravitation field. So today we will continue this gravitation field discussion, and in particular we will talk about what happens when two sources of gravitation exist in the space, either fixed or moving. But before doing that, let me just remind you some simple things and simple formulas, basically. If you have a fixed object of mass m and a test object of mass lowercase m, then the force of gravity which this test object is experiencing is actually equal to, well, by magnitude, by modulate, it is equal to g times m and divided by r squared, where g is universal gravitational constant and r is the distance between them. Now, and obviously it attracts, so the force direction is from lower case m to capital case M, and this is its magnitude. I would like to actually express it in a vector form, and here is how we can do it. Let's say this is vector of position. So if our fixed point is the center of the coordinate system, then r, which basically depends on time, because this object will be moving back and forth. So in this case, this is a position vector, position. Now, if this is the position, vector of force is collinear, because it's in the same, basically, line, but in an opposite direction. So to express it in form of this, I can do it this way. F is equal to minus g m, and I will multiply it by vector r. Now, to neutralize change in the magnitude, I will divide it by vector r. So that will be my unit vector in that direction. And then I will continue dividing by r squared. So it would be r cubed. So this is a better formula in the sense that this is the vector formula. This is just scalars. Okay, so that's one thing. Another interesting thing is, I would like just to remind you the concept of a potential. Potential of of the field is amount of work which field is supposed to be performed when it moves some test object of a unit mass, when lowercase m is equal to 1, unit mass from infinity to some point. So that's a potential at a point. So it's work. Now, from this we actually discussed a few consequences. For example, that work to move an object from one point to another by gravitational field does not depend on the trajectory, only on the endpoints, because basically it's a difference in potentials times mass. So that's very important part. And also what's important is that the gradient of potential u of p. So the gradient of potential is basically the intensity of the field. Intensity means force per unit of mass. And the gradient, if you forgot, is basically a vector of partial derivative. Now, moving from single source of gravitation to two sources, our first problem is, okay, what happens if we have two sources, fixed sources somewhere in space, and we are measuring the force and the potential at any point. So you have MA and you have MB. So the force goes this way. So this is, let's say, point P where we are measuring. This is point A, this is point B. So now the forces which are acting on the same object, if you would like to actually find out what's the result, we have to add them as vectors. At the same time, since the force is can be represented as gradient of potential, so if you will measure separately potential of field which is produced by this mass at point P, and you will have a field from capital MB produced at the same point. These are two potentials. They are added together to get a total potential. So potentials are basically can be summed up exactly like vectors of forces, but it's simpler because potentials are scalar, and the vector of force is field intensity actually is the gradient of this. Now the gradient is a set of partial derivatives, and derivatives, the operation of taking a derivative is additive. So that's why if you will add these, you will have the total force. These are partial potentials, and you will add them together would be a total potential. And again, differentiating this, and this will give you the same equivalent between intensity. Intensity is also related to, these are vectors. Intensity, again, that's the force per unit of mass. So that's kind of easier to work with potentials, just as a reminder. But in case of two objects fixed at some position, and we are measuring the field somewhere in space, the field which is the result of two different gravitational fields which are superimposed on each other, then the forces are added together and potentials are adding together. Now there is another problem related to two objects. Now in this case I was saying, so let's say we have two objects at fixed position, and we are measuring the field which is produced by superposition of these two fields. Now I would like to do different. I would like to find out how these two objects can move if they are not fixed. So both of them experience the force of another. So if you will take one object, MA, and its position would be RA depending on T. Position relative to some coordinates, and R is a vector from the origin of these coordinates to a point where this particular mass is located. So if the point is A, depending on T, then OA is the vector we are talking about. This is RAT. Now we have another point, MB. It's at point B, depending on time, and RBT is a vector OB. So the position is changing. So points A and B are somewhere moving. Now, what can we say about the force which is which A experiences because of the gravitation of B object. Well, that's obviously minus G MA MB and divided by distance between them. Well, distance between them, if you wish, that's basically RB minus RA, these two vectors, and you have the modulo. That's the distance square. Okay, now let's talk about the force which is from B to A. Well, it looks the same, but here you have to put RA minus RB. Now, while here it looks exactly the same, but this is not a good thing, because this is a vector and this is a scalar. To make it a little bit better, you have to put cube here, but multiplied by, okay, let's do it differently. Multiplied by RB minus RA divided by vectors, divided by RB minus RA magnitude in a third degree. And same thing here, but the direction would be different. RA minus RB divided by RA minus RB cube. Now that's much better because these are vectors and now these are vectors. Now what's interesting is that obviously these two are opposite to each other and their sum is equal to 0, right? Because everything else is the same. So FAB vector plus vector BA, both of them are function of t because location is changing, right? So R is changing. It's all function of t. All function of t. Masses are constant, but location are different at every time, so this is all function of t. So this is equal to null vector. These vectors are equal in absolute value, in magnitude, and opposite in direction because this is RB minus RA, this is RA minus RB. Okay, so far we know this. What's next? Next is a very interesting statement that no matter how these objects are moving around each other, they're passing each other, whatever it is, if there are no other forces which affect their movement, then my statement is that the center of mass between these two, there is a point which is called center of mass, I'll bring the definition, is not experiencing any kind of a force, which means it moves with a constant velocity along the straight line, uniformly moving. Now, these are two vectors and their sum is equal to 0, right? Okay, now, what is the definition of a center of mass? Well, I'll just give you a definition of exact the point. Let's call it R of t, well, depending on t. That's MA RA plus MB RB divided by sum MA plus MB. That's a location. If RA and RB are equal to each other and opposite in direction, then you will have location exactly at center of coordinates. So no matter where it is, if you have, well, let's talk about this plane instead of the 3-dimension. Even on the plane it's kind of obvious. If you have two objects here and here, this is a more massive object, and this is the less massive object. Where is the center of mass? It's on the line which is in between them, but moved towards more massive object. So proportionally it should have, now the middle line is RA plus RB divided by 2, right? That's the middle line. But if objects are equal to each other. Otherwise you will have some, it's basically equivalent in mass, but put into the average mass, put into middle point between them. But if one mass is more massive than another, then the center of mass would be shifted towards something. Okay. Now, what else? Well, if only one mass exists, let's say there is no mass, capital M, then we are supposed to have coordinates of the center of mass exactly where the only mass is, right? So if there is no MB, we will have MA would cancel each other, we will have that R is equal to RA, or vice versa. So basically this is a definition of center of mass. And now let's just see what happens with the center of mass. Let's just differentiate it twice. Second derivative. Now if R is a position of some point, then the first derivative is velocity as a vector, by the way, and the second derivative is acceleration. So this is acceleration of the center of mass. Okay, but let's just think about this. What is this? This is mass times acceleration of the A object, which means, according to the second law of Newton, it's force which acts on the first object. Same thing here. Mass times acceleration, mass the second object times acceleration, that's the force which acts on the second one. But the first force is the force from object B to object A, and the second is from object A to object B. And they are, as we know, are nullifying each other. So the second derivative would be equal to 0 divided by MA plus MB, which is 0 vector, which means what? If acceleration is equal to 0 vector, that means that there is no acceleration, which means there is no force, there is no acceleration, and the according to the first law of Newton, we will have this center of mass moving in space uniformly along a straight line with a constant velocity. And that's what I wanted actually to show. So if you have, let's say, two different objects, and they might actually do something in space, let's say a moon and the Earth, if there is no other sources of gravitation like sun or other planets or whatever, then they would move somehow, but their center of mass, which obviously is close to the Earth, because Earth is much more massive than the moon, but this particular point will move along a straight line with a constant speed. Again, if there is no sun. Sun actually makes the whole thing different, because now we are supposed to both rotate around the sun. Now, very kind of approximately, we can say that the moon and the Earth are rotating against each other or around each other, but not really around. It's not moon which is rotating around the Earth. It's both moon and Earth are rotating around the center of mass, which is very, very close to Earth because Earth is heavier. But anyway, it's not exactly the center of Earth. Moon is not rotating around the center of Earth. Moon and Earth together rotate around the center of mass, which is close to center of mass, center of Earth, but it's not the center of mass. Okay, so that's it. I suggest you to read the notes for this lecture. They are presented on unizor.com. You go to the Physics Plus course. The chapter is called Laws of Newton, and this is the gravitation of two objects. That's the name of this lecture. So we had two different kinds of problems. One is with two fixed objects, and we were measuring the gravity at some point, or we just have two moving around each other objects, and we have proven that they're actually moving in such a way that the center of mass is moving along a straight line with constant velocity. And if our inertial coordinate system, inertial reference frame, is basically such that we position it at the very center of mass between these two and let them do whatever they want, then this point will remain in place, basically. It remains as at origin. So if in the very beginning we put our inertial frame in the center of mass, then the center of mass will stay still, basically. Okay, so that's it for today. Thank you very much, and good luck.